Hello friends, welcome back to Techmine Guru. I am Supratim and today we are taking a massive leap in our DSA journey. We are moving beyond simple traversal. Today we are going to cover arrays part 4 where we will learn the carry forward technique and the deep logic behind subarrays. Often students ask me, sir, I made the brute force solution, but how do I optimize it? The answer lies in today's session. So what is our path today? First, we will master the carry forward technique, learning how to solve pair problems. Next, we will understand the math behind subarrays. And finally, we will fight a boss battle where we will find the smallest subarray with min and max elements, which we will try to solve in O of n. So we are moving beyond simple traversal. Today, we will learn how to carry data with us to solve problems instantly. So let's start with a challenge. Look at the string on your screen. We need to count the pairs I comma j such that I is less than j and s of I is equal to a and s of j is equal to g. So given a string s of lowercase characters, return count of pairs I comma j such that I is less than j and s of I is equal to a and s of j is equal to g. So we have to count ag pairs, right? So for example, if we see what all are the ag pairs here. So one pair will be 4 comma 5, one pair will be 0 comma 3, and one pair will be 0 comma 5, right? So the answer will be 3. Let's see one more example. We have given a string s is equal to b, c, a, g, g, a, g. So how many pairs are there? One is this pair, this a and this g will make one pair, and one this a and this g will make pair, and one this a and this g will make pair. Can you find one more pair? Yeah, definitely. One pair is this one with this one. So how many pairs in total? So 2 and 3 will make one pair, 3 and 4 will make one pair, 6 and 7 will make one pair, 5 and 7 will make one pair, and 2 and 7 will make one more pair. Similarly, if you see this example, 1 will make pair with the 3, 2 will make pair with the 3, 1 will make pair with 7, 2 will make pair with 7, and 6 will make pair with 7. So the answer will be 4, right? So how does our brain usually think? If we approach for the brute force, how we will think in this manner? So we will think for every A, let's scan the entire right side to count number of G's, right? So for this thing, we have taken an answer variable so to keep the total number of counts. Now we are iterating from for I is equal to 0 to n minus 1, and we are checking if we get an A or not. Once we get an A, from that index onwards, we will start a second loop where we will run from j is equal to I plus 1 to n minus 1, and we will check whether s of j is g or not. And whenever we will get s of j as g, we will increase the answer. So basically, for every A, we are scanning the number of g's present in the entire right side starting from that A. So what if the constant here is n is equal to 10 to the power 5? Then in that case, we will get n square as 10 to the power 10, which is not lesser than 10 to the power 8. So our this code will give a TLE, right? And since we are not taking any extra space, extra array or something like that, our space complexity is O of 1 and time complexity is ON square, right? But at this constant, our code will not pass. So we need something better than this, right? Let's analyze how we can find something better. So imagine if we start from end of the array, from right to left, and whenever we hit the last G, we know we have seen 1G. When we are going to encounter the next G, the count becomes 2. But in this, as soon as we find an A, we don't need to check ahead. We already know how many G's are on our right side. So we will directly add that count to our answer. So this will be our optimized approach to solve this problem. So for this, we will keep two variables. One will count number of G's present in the string, and second will count the total number of pairs we are getting. So we are starting from the right side of the array. So we reached G, we will count G as 1, right? When we will move to A, that time we know that we have already 1 G counted. So our answer will be answer plus number of counts of G. So answer will be 1. Similarly, when we proceed here, we will get another G. Now count of G becomes 2. Now when we will move towards A, we have 2 G's present here, which will make 2 pairs, right? So we will add this number of G's in the answer itself. And then we will keep moving towards the left. And again, we will do the same thing for this A as well. So here also we will see the number of G's. We will add up the previous count of G with the current answer. So for this example, if you see, if we started from G, our count of G will be equal to 1. In K, we don't have to do anything. Then we will move towards the A. Our count of G present is 1. The answer will be answer plus C. Then answer will become 1, right? Then we will move again from fourth index to third index, where we will find another G. So our count of G will be 2. And previously in the answer, we have already got one pair. Now, when we will move again to the left, we will come across again one A. So previously our answer variable was having one pair as the answer, but now we have two G's present already. So our answer will be answer plus C. That means we have got 3 pairs of G. How? One will be the this pair, one will be the this and the this pair, and another will be this and this pair. 3 pairs. Similarly, still keep moving towards our left. We will encounter again G. Our C will become 3. And previously we have in our answer as 3. So again, when we will move to A, we will add the number of G's in the present answer, which will make our as 6 pairs. How? Because till here we have got 3 pairs, right? So when we will move here, it will be a 4th pair, but this A will again make pair with these 2 G's, right? So total count will be 6. So let's see the code for it. This is a simple code in which you can see that I have started the I loop from the end of the array, going from n-1 to 0. Then whenever s of I is equivalent to G, we are increasing the count of G. And whenever we are encountering A in the s of I, we will add the count of G to our present answer. And like this, we will continue in our loop. Let's look at the performance. So time complexity, as you can see, I have run one for loop only. So time complexity will be O of n. And I have not taken any extra space, any extra array. Only 2 variables I have taken. So the space complexity will be O of 1. So now let's move on to subarray. So what is a subarray? A subarray is a contiguous part of an array. For example, if we have an array 4, 1, 2, 3, -1, 6, 9, 8, and 12, is it a valid subarray? 2, 3, -1, 6? Yes, because they are in continuation. Can we say the single element in this array is a subarray? Yes, definitely. Single element is also a subarray of itself. And similarly, if we consider the complete array also, the complete array, full array, is also a subarray of itself. But these are some invalid subarrays. For example, if we have given 1, 2, and 6, since they are not contiguous, they are not valid subarray. Similarly, if we have 3, 2, 1, 4, the orders should be same to consider it as a subarray. So 3, 2, 1, 4 is again not a valid subarray. So what is the subarray representation? So subarray can be uniquely represented as start and end index of the array and start and length of the array. So suppose in the given array, we have given start as 3 and end as 6. Start at 3 and end at 6. So our valid subarray will contain from 3 to 6. Or it can be given that start is 3 and the length of the subarray should be 4. So if we start from 3, what will be the length of 4? 3, 4, 5, 6, and 7, right? So our subarray will be 3 to 7, right? So now let's understand how to calculate the total number of subarrays. So let's start here. We will keep the start index as I, and we will see how many subarrays starting with the index I is equal to 0 is possible. If we start with 0, end index is also 0, we will get a 4 as a subarray. If when j becomes 1, 4, is also a subarray of it. When j equal to 3, 4, 2, 10 will be also a subarray. Similarly, when j is equal to 6, complete array will be a subarray. So if we start that from I is equal to 0, then we get n subarrays. So if we try to generalize the same thing, we will see a pattern here. So when we will start for I is equal to 1, we will get n-1 subarray. Similarly, when we will start from I is equal to 2, we will get n-2 subarrays till we reach the end of the array, which is I is equal to n-1, where we will get 1 subarray. So what is the total number of subarrays? We have to add all of them. So when we will add all of them, we will get n plus n minus 1 plus n minus 2 up to 1. So total subarrays will be n into n plus 1 by 2. This we have already learned in our previous lecture, right? So what if the question says print subarray from start to end? So nothing we have to do in that. We will be given the index start to end. We will run a loop from start to end and we will print it. But what if the question says print all possible subarrays? So from here, we learned how many total subarrays are possible, n into n plus 1 by 2. But to print any subarray, start to end index, we have to print it in the time complexity of O of n, because one for loop is there, right? So if we have to print all possible subarrays, then we have to do it in 3 loops. One for I is equal to 0 to n minus 1, which will define our start index of the array. Then j is equal to I to n minus 1, which will define our n index of the subarray. And then running a loop from k is equal to I to j, which is like start to end, and to print the array. And here we are printing a new line so that all the subarrays we get in a new line. So the total complexity will be O(n) square, which is for calculating total subarrays, and O of n for printing particular subarray. So our total time complexity will be O(n) cube. So can we solve this question better than this? No. Remember guys, printing of array or subarray or a matrix will take its usual time complexity, and that will not be a part of an online IDE. So we don't have to worry about it. So our total time complexity will be O(n) cube, and since we are not taking any extra space, so that is why our space complexity will be O of n. Now let's move on to the last part of our lecture, where we will see a boss level question. So here in the question says, find the length of smallest subarray containing both minimum and the maximum element. So for example, if you see, if A is equal to 1, 2, 6, 5, 4, 1, what is the minimum element in this array? 1, right? And what is the maximum element in this array? 6. And we have to find the smallest subarray which is containing both of it. So if we consider this subarray, we will get a length of 3. What if we consider this subarray? This is also consisting of 1, right? But here our length will be 4. But we have to get the minimum length of the subarray which will contain both. So our answer will be 3 only. Let's start with the brute force approach. I have not written calculating minimum and maximum element of an array, but it seems very easy to check whether it is a minimum, how to find the minimum and maximum element. So in this, we have already found out the minimum element as mi and maximum element as ma. So what we are going to do, just as we saw earlier, that for printing a subarray, we are starting with the I index and moving towards the j index. So similarly, we are doing here also. We are running a loop where we are keeping I is equal to 0, which will define the start of the subarray, and j loop, which will define the end of the subarray. And when we are iterating over the subarray, we are using a for loop of k, which is moving from start to end, that is I to j. So we will keep checking if a of k is minimum element or not. If we get a minimum element, we will take 2 Boolean variables in this solution, minimum of p as false and maximum of p as false. And wherever we will get the minimum element, we will mark that we have got the minimum element as true. Similarly, if a of k is maximum element, we will mark it as true as well. And once both minimum and maximum we get, we will calculate the length. So I have taken the minimum function so that we can get the length of smallest subarray. And how to find the length of subarray? As we have learned in our earlier class, that if we want to count the number of items present in the range I comma j as b minus a plus 1, so that will give us the length of the subarray. So since we see that we are running 3 loops, our time complexity will be O of n cube, right? And to find the minimum and maximum element, our time complexity will be O of n. So n cube will be the dominant factor, so our time complexity will be O(n) cube. And we are not taking any extra space, so our space complexity will be O of 1. So can we optimize it little further? Definitely. So what can we do in the optimization? Let's observe one thing. Whenever we have an array, suppose we have this array as 1 and we have to count the minimum and maximum. Can we fix the start position and not move it? Because every time what we are doing is that we are taking this, then 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 we are taking this, and similarly we are taking this, then 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 we are taking this, right? So what if I fix the start index and I keep moving the j index? Will it cover all the array? Definitely. And it will also tell that we have reached any maximum array or not. In this way, this loop will not be needed in that case. So in our optimized solution, you will see the same thing. So we are fixing the I from 0 to n minus 1, and we are just moving the j from I to n minus 1, and the remaining logics remains the same. We take two bool variables as min p and max p as false, which will tell us whether we got the minimum element or not, or we got the maximum element or not. And the remaining logic remains the same, where we are checking if a of j is minimum element, we will make min of p as true. If a of j is maximum element, we will make the maximum element as true. When both of them are true, then we will find the min of answer till that position. And for counting the length of the subarray, the formula is b minus a plus 1. Since we already know that if we have to find the number of elements from a to b, this is the formula we generally use. So since we have removed one of our loop, so our time complexity is becoming as O(n) square, and our space complexity will be again O of 1, since in this also we are not taking any extra space. But guys, if you observe more, you will find more optimized solution than this, because the brute force code will work only if n is in the range of 1 to 10 to the power 2 or 3, right? Similarly, if our range is 10 to the power 4, this code will also work. But what if our range is somewhere 10 to the power 7? This optimization will also not work in that case. So we are coming back to the final optimization. So where we have to do two observations mainly. First thing, in any subarray, there will be only one maximum element and one minimum element. Why? Because if any other minimum or maximum element is present in between, then our size will decrease. Then our length of subarray will change, right? So if we get a smallest subarray in the final answer, we will get only one maximum element and one minimum element. This is the first observation. And the second observation which you have to do is that the min and max element will always be in corners, and we will not worry about the middle element. So what are the possible arrangements in case we get one minimum and one maximum? So min can be at left and max can be at right, or max can be at left and min can be at right. So our approach will be, for each minimum, we will try to find closest maximum in the right. And similarly, for each maximum, we will try to find the closest minimum in the right. So we will write the condition for both the things. So before writing the code, let's understand with an example. So let's take an array 2, 2, 6, 4, 5, 1, 5, 2, 6, 4, 1. What is the minimum element in this? 1, right? And what is the maximum element in this? 6, right? And how many such elements are there? So 6 here also present and 1 is here also present. So what do you think? What is the minimum length? This will give us 3, this will give us 4, and this will also give us 3. So the smallest subarray is this one only, right? Which is 3. So let's understand that with this tabular data. So initially, the min index and max index, you can keep it as -1 each. So we will again start the loop from the end of the array. Since we understood that this is a minimum element, we will update the min index from -1 to 10, right? We have still not got the maximum index, so that's why it is -1. So what will be the answer of the length? 10, 10 minus 1 plus 1, which will be 11. Similarly, when we move to 9, this is not the minimum also, this is not the maximum also. So we will not update any of the previous index. So similarly, when we will move to 8, we will see that 6 is our maximum element. So we will update the index. So from -1, we have got a maximum index as 8, right? So previously in our answer, what was the length? 11, right? So we will check what is the length of the subarray now. So now it will be minimum of 11, comma, minimum index minus maximum index plus 1, which will give us the length of the array. So it will be like mod of this. Mod means we have to take the absolute value. So it will be 10 minus 8 plus 1, which will be 3. So minimum of 11 and 3 will be 3. Similarly, when we move to 7, 2 is neither a minimum nor a maximum. Similarly, when we will move to 6, 5 is not a minimum or maximum anything. So we will skip the 6 also. Similarly, when we will move to 5, we will see that 1 is again a minimum element. And now our current min index will change. So our current min index will be now considered as 5. So now our minimum will be 3 comma, what is the max index? 8, right? 8 minus 5 plus 1, which is again 3 only. Similarly, we will move to 4, nothing will get changed. Similarly, we will move to 3, nothing will get changed. Similarly, we will move to the index 2, where we will get a max element, right? So we will update our max index as 2, since 6 is sitting on the index 2. So what will be our minimum length? Min of previous answer 3, comma, min index minus max index plus 1, which is 3 again. So whatever we will do, we will get the length of the array. So 5 minus 2 plus 1 will give us 4, and minimum of 3 and 4 is the 3. So this array will be our final array, which will give the minimum length of subarray having minimum and maximum element both. So let's see that in our final code. So we are taking min index as -1 and max index as -1 initially, and we are assuming that the length of the array is the length of the answer. So we are starting the loop from the end of the array for I is equal to n minus 1 to 0. Then, since we have already calculated mi as a minimum element and ma as the maximum element, we will use that thing in our code. If a of I is minimum element, we will update the min index, and then we will check, did we already got our max index? For now, no, right? So if you have not got our max index till now, that means max index is still -1. So this if will not work. Now we will check for that index that whether we have got a max or not. Since for that index we have already got the min, so this condition will also not work for the first iteration, right? So now we will move to 4. For 4, we will see this is neither a minimum element nor a maximum element. So nothing will get changed. Then we will move to 6 again. When we will move to 6, that time a of I is not minimum. So this condition will not work, but this will work, right? And it will update the max index. So it is updating here as 8. But previously, while iterating, we have already received our min index also. So now our min index is not -1. So now can we find the length? Yes. The length will be minimum index minus maximum index plus 1, and answer will be min of answer and length. So in this 2 if condition, just we have to change max index minus min index plus 1 at one place, and in another place min index minus max index plus 1, so that we can keep the length as positive. So that's why we have made these changes. So what if we would have got initially this one as 6, this one as 6, and this one as 1? In that case, firstly, when our loop will run, this if will not run, this if will come and it will update the max index, and it will see min index is not equal to -1 or not. So at that time min index will be -1. So this will also not work. So then we will move to the other element, which was 4, right? We will see it will not match to any of the minimum and maximum element. We will skip that element. Then we will move again to this variable, which is now 1. So this condition will work, and it will update the min index count, right? And now we already have the max index as 10 set. So this condition will also work, and it will find out the length, which is max index minus min index plus 1. And the answer will be answer, comma, length of this subarray. So this will always give you the minimum between the two lengths. So what is the total time complexity? To find maximum and minimum element, it will be O of n. For this code, we are already calculating everything inside one for loop only. So it will be also an O of n. And so his min function will tell whether this which is the minimum from these two variables. So it will be O of 1. So what is our total time complexity? O of n plus O of n plus O of 1, which will be O of n. And since we have not taken any extra space, our space complexity will be O of 1. So did you see how we optimized our code from O(n) cube to O(n) square, and then by seeing some special patterns, we have optimized it further to O of n. So this is a lead code problem. I have given the link in the description as well. So congratulations, guys. Today you have leveled up again. So here is the quick recap what we have learned today. So we have learned about carry forward, where we learned that by iterating backward, we can perform O1 lookups. We have learned about subarray math, where we understood the n into n plus 1 by 2 logic to avoid brute force. And we also tracked indices to win the boss battle. So now you don't loop blindly. Now you see patterns and reduce complexity. In the next episode, we will talk about contribution techniques and sliding window problems. These are the techniques that unlock constant time range queries. If you learned something new today, subscribe to the channel. My name is Supratim, and I'll see you in the next one. Signing off for today. Till then, keep learning, keep coding, keep optimizing.